Okay, a couple of the theorems that were talked about in the videos, the intermediate value theorem and the Rolle's theorem. We will use both of those to answer this question, or to show this equation, x cubed plus x minus 1 equals 0, has exactly one solution. Now, first of all, what that means is a solution exists. There may be more than one solution, but there's at least one. And then exactly says, well, there's a solution exists, but there's only one solution that exists. There's not two or three. So, kind of taken in two parts, we'll be able to show that there is one and only one solution to this equation. Now, this equation actually comes from our worksheet on using Newton's method. Problem number 3 on Newton's method, approximating. We went through Newton's method to at least approximate that solution. But we're going to show that that is the one and only one real solution for this equation. Now, we do throw in real solution because there could be, and actually theoretically there will be, two other solutions, but they're complex solutions. You remember our quadratic equations, sometimes we end up with complex values, square roots of negative numbers give us the I. We'd have plus or minus I as part of that solution. So technically this solution will have this equation will have three solutions, but there's only going to be one real solution. The other two would be complex, and we're not going to worry about what those complex solutions are, thank goodness. Okay, but we're really not even going to show what the solution is. We're just going to show that there is one real solution. Now, first of all, the intermediate value theorem is actually fairly easy to show that there is at least one solution. If we look at our function, and we could say, let's just choose some values. If x is 0, f of 0 would be what? Okay, negative 1. Well, let's see. How about if we choose f of 1? What's our y value going to be? Okay, it would be positive 1. Now, sometimes we have to do a little more work than this, but 0 is always a good place to start. 1's always a next best place to go. And because f of 0 turns out to be negative, and f of 1 turns out to be positive, then we are guaranteed, well, one other condition on this, our function must be continuous, which a cubic polynomial will be continuous. There's no holes or jumps. Okay, it's a nice continuous curve. Well, if we kind of look at the idea of the graph, 0, negative 1, we put our point here, and then 1, positive 1 would put another point here. We are looking for the x value that gives us a y value of 0. That x value is going to be somewhere in between 0 and 1, because the graph of this would have to go through this point and would have to go through this point, and since it's continuous, would go somewhere through the x-axis, through y equals 0, at some x value between x equals 0 and x equals 1. It might be like that, or it might be like that. Okay. We don't know exactly where it is. We just know it's somewhere in between 0 and 1. And the intermediate value theorem doesn't say it's just one value that's in between there. Technically, it may do something like that, where we'd actually end up with 3 solutions in between 0 and 1. Well, the intermediate value theorem tells us there's at least one real solution, and that real solution is going to be somewhere between 0 and 1. But now we're going to use the Rolle's theorem to say, well, it's not just at least one, but there is exactly one. No more, no less. Okay. So let's take a look at how we do that. Now, to be able to show there's only one solution, or a lot of times in proving things in mathematics, we have to make some assumptions, and then we're actually going to show that those assumptions are wrong. So if those assumptions are wrong, then the reverse of those assumptions must be correct. Okay? So that's kind of the basic idea where we're starting. Now we know that f of 0 was -1, f of 1 was +1. So there is at least one solution between these two values. Let's assume, here's our assumption, let's assume there's 2 solutions in the interval from 0 to 1. And let's just go ahead and say C sub 1 and C sub 2 will be those solutions. Or in other words, we look back to the function form that we're looking at. That would mean f of C sub 1 equals 0 and f of C sub 2 also equals 0. Okay. Maybe that's 0.2 and 0.6. Well, we don't know what they are, but we're assuming that there's 2 solutions. Now, Rolle's theorem because of this assumption, we can show f of C sub 1 is equal to f of C sub 2. Okay, both values are equal to 0. And the conditions that occur with Rolle's theorem, f is continuous, which we already talked about using continuous function for the intermediate value theorem, and Another criteria for Rolle's theorem is that f is differentiable in the interval. Well, quick look at this. The derivative of this is going to exist, well, basically for any x value. So Rolle's theorem says since all of these have been met, then there is at least one x value in this interval in between our two solutions such that f primed of x equals 0. Okay, again, the conditions on Rolle's theorem. C sub 1 and C sub 2 have the same y value. In this case, we're saying if they're both solutions, the y value would equal 0. F is continuous, f is differentiable. Then we are guaranteed somewhere between C sub 1 and C sub 2, there's an x value with the derivative equal to 0. Okay. Well, let's take a look at what our derivative is. X cubed plus x minus 1 has what derivative? Derivative of x cubed is 3x squared plus x, derivative of x is 1, minus 1, derivative of a constant is 0. So this is our derivative for our original function. And Rolle's theorem says, well, somewhere in between C sub 1 and C sub 2, there's a derivative that equals 0. But what's going to happen as we try to show where x equals 0, or what x value makes y equal 0, I guess I should say. We can subtract 1 from both sides, divide by 3. X then would be positive or negative square root of negative 1/3. Is that a real number? No. Square root of the negative would give us I times the square root of 1/3, or square root of 1 over square root of 3. We'll just put it that way since, again, I'm running out of room. But the point here is, this goes against what we were supposed to find. Based on our assumption that we made, C sub 1 and C sub 2 are both solutions to this equation, then we should be able to find an x value where the derivative is equal to 0. But we're not finding that. We're finding complex solutions, but no real solutions. So something must have been wrong, and, well, we've proven that our assumption was not correct. Remember, we assumed two solutions . Well, the only thing we can deduce from going through all this, Rolle's theorem does not work based on what we've said, and the only thing that would be wrong then is our assumption. So therefore, there is not two solutions which brings us back to what we're trying to show. There can only be one solution. And again, technicality here, one real solution. So through the use of the intermediate value theorem, we said there's at least one. Through the use of Rolle's theorem, there is only one, or there's not two, I guess. Not two. Well, if there's at least one and not two, then that has to be one. Exactly one solution, one real solution between 0 and 1 for this, well, actually we could say for any of the x values, but exactly one solution to this equation. Okay? Questions there? Okay, we'll take a look at what this mean value theorem is and how it's actually used, one application of it anyway. Not that you would be using it, but maybe a police officer that stops you for speeding may be using this. He or she probably wouldn't know they're using this, but this is why it works. But let's kind of hit the basics first, and then we'll take a look at how this is applied. Okay, mean value theorem says, well, there's some point A, f of A, and some other point B, f of B. And we have this function f of x, whatever it might look like. The mean value theorem says, again, the function must be continuous and differentiable between A and B. And the mean value theorem compares the slope, oops, make that bigger up here. The slope of the line between our endpoints and the slope of the tangent line at certain other points. The mean value theorem guarantees at least one point in between A and B, at least one point, we'll call it C in this case, where the slope of the tangent line, or technically the derivative value of C, equals the slope of the line through the two endpoints. Well, as we kind of look over the curve, there's actually going to be a couple different points that fit that. Looks like there's one of those. And then, well, my graph isn't real great here, but probably about right in there. Let's focus in on this one. This side gets a little too ugly. It's a good thing I don't teach art. But anyway, you can see visually they look like parallel lines. Parallel lines have the same slope. Slope of the tangent line at this point C will be equal to the slope of the line through the two endpoints. Now, derivative, we're looking at it in terms of slope of a tangent line. But derivatives can also represent velocities. Okay, if we're dealing with a, say, position function, and the derivative of the position function is velocity, speed. This is how you may actually get a speeding ticket. to be able to tell how fast a vehicle is traveling, police officers clock the car, the vehicle, and let's say that you are clocked, you're timed at 48 seconds in 1 mile. Well, you're given a ticket for speeding. How fast would they be able to show that you were going? Now, you may not be going the same speed the entire mile, okay, but they can still say, well, you were at least going this fast. Maybe you were going even faster at some point, but we can prove that you were going at least this fast. This is using the mean value theorem. Your speed at some particular point, at some time in that 48 seconds, is going to equal the, well, this is technically the average velocity. This formula we would use for the average velocity from time 1 to time 2. So from, I guess we'd be saying t equals 0 to t equal 48. Let's write up some points here. T equals 0, our position, well, we would be saying we're going to start at position of 0. And then at 48 seconds, we're going to be at a position of 1 mile. Okay. So the average velocity then would be change in distance over change in time. Well, that looks like a very small number, but yet you're going to get a speeding ticket. What units do we have here? Okay, miles per second. 1 mile in 48 seconds. How does that convert to miles per hour? What do we need to multiply by?
From 60 seconds, like, we just like stroke down.
Okay.
60 seconds.
60 seconds per minute.
Yeah, 60 minutes.
60 minutes per hour. Now, you can do it this way, or you can go directly. 60 times 60 is 3,600. 3,600 seconds per hour. Okay, but notice unit cancellation, second divided by second, minute divided by minute, and we're left with miles per hour. So numerically, we'd have the 3,600 divided by 48, and that's going to be what? Well, that simplifies to 75. Now, again, this doesn't say that you're going 75 the entire time. All that can be proven is that you were going 75 at some point during that 48 seconds. Now, some roads you have a 75 mile an hour speed limit, but in the smaller highways, more like 65. So you would get a speeding ticket, at some point in that 48 seconds, you could theoretically be going 90 miles an hour. But hopefully you would have slowed down really quick. But again, the only thing they can prove, if they're timing you, if you're clocked, they could say, well, you were at least going 75 miles an hour. Okay? And that's using the, theoretically using the mean value theorem. Hopefully you won't have to face that, but that is a possibility. Drive safely, drive within the speed limits. Now you can explain, if you ever do get pulled over for doing that, and they say you were clocked at such and such, you can explain the calculus behind it. They might keep writing the ticket, but
Might give you a bigger ticket.
yeah, it might give you a bigger ticket. But any questions on that?